Right. Hello guys. This will be the fifth video in our integration section. So the previous video, 15.4, is on the application of double integration, in particular on probability. And in this section, we're going to introduce another application, which is the surface area computation. So basically, yeah, you're given a surface and want to compute the surface area above some certain region. In this case, I drew a square, but it can be arbitrary domain. So in this particular section, we'll be investigating surface area of graphs. So every surface looks like z equals to f of xy. However, for more complicated surface area, we will require some sort of parameterization. And that technique will be introduced in section 16.6. So this is sort of a foreshadowing of what we're going to do in chapter 16. But anyway, let us first start with the computation of this type of easier surfaces, the graph of a continuous function. Okay, so let's derive the formula first. Given a surface given by a graph, z equals to f of xy, we are interested in, say, in this case, a region of surface above a domain omega. And the idea of computing the surface area is quite simple. We again partition this omega into several grids. So say omega is equal to the union from I equals to 1 to n, j equals to 1 to m over some square. xi minus 1, xi, yj 1 minus 1, yj. And this is rij, right? This small square here. Okay. Now we project this guy up to the surface and we get a small region on the surface, which we can compute. So let us denote that small surface by Sij. Okay. So how do we compute Sij? Let us look closely on this small surface area Sij. So when n and m are large, meaning that your mesh is really, really small, you partition your small domain omega into very, very fine pieces. In that case, this guy actually looks like a parallelogram, right? Because the slope, the curvature is almost zero. It almost looks like a flat surface. So we can understand this guy as a parallelogram somehow when the mesh is so small. In that case, let us first note the vertices of this parallelogram. One is obviously xi, f of xi, yj. And obviously this will be xi plus 1, yj plus 1, f of xi plus 1, yj plus 1. Similarly, going above, you have xi, yj plus 1, f of xi, yj plus 1. And the bottom right will be xi plus 1, yj, and the corresponding function value, f of xi plus 1, yj. Now, as I mentioned, the distance between these sets, this parallelogram, is quite small, so you can approximate this guy by its linear approximation at the point f of xi, yj. So basically, this guy will be f of xi, yj, and you multiply it by the slope along y, right? So that is the derivative of f with respect to y, plugging in xi, yj, multiplied by the differences between these two values, which is yj plus 1 minus yj. For convenience, let us denote that by delta yj. Similarly, for this data point here, you can evaluate this guy using a linear approximation. So it is locally looks like f of xi, yj plus fx xi, yj multiplied by the differences between this guy, this guy and this guy, this guy and this guy, this guy and this guy. Sorry. So actually, I'm not sure why I did this incorrect again. This should be xi plus 1 minus xi. And again, let me denote this by delta xi, okay? Right, so we now know that this vertex locally looks like this guy when the mesh is so small. And similarly, this vertex looks like this guy. So to compute a parallelogram, in this case, I drew a square. It should be a parallelogram. To compute that parallelogram, the area, we can use the cross product, right? We have learned this in section 12.3, I think. So the area for this parallelogram can be computed by this the magnitude of the cross product between this vector and this vector. So first of all, what is this vector? It is given by differences between this vertex and this vertex, right? So you have xi not moved. Sorry, I use v first. So that is do this guy first. You have xi plus 1 together with xi. That gives you delta xi. And yj doesn't move. The differences between f and the function value here is given by fx, xi, yj, and delta xi. The same thing happens for the u vector. You have xi unmoved, so 0, and yj goes to yj plus 1, so that is delta yj. And f of xi yj goes to fy xi yj multiplied by differences, plus the original value. So this will be your difference going here. So doing cross product, the component for I is this guy multiplied by this guy, which is 0, minus this guy multiplied by this guy. If we factor out the delta xi, delta yj, you'll get this thing outside and minus fx in the first coordinate. For j, you have minus this guy times this guy plus this guy times this guy. So you have this guy in your bracket, minus. For the last coordinate k, it is basically this guy multiplied by this guy. And you factor out this common factor, so you only have 1 in the last coordinate. Doing Pythagoras theorem, you will get fx squared plus fy squared plus 1 with delta xi, delta yj. So we know that the whole surface area looks like the summation over all grid of A Sij. This is the area of that small surface area. And we had computed above that this thing looks locally like a parallelogram, and that parallelogram can be given by this formula, which is here and here. And let us know that this delta xi delta yj is simply the local area here, right? Rij. So this is a Riemann sum, right? That looks like a Riemann sum. And so it converges when the mass goes to 0, this integration over omega. Omega is the domain that you're interested about the surface on. And the integrand would be fx squared plus fy squared plus 1 dA. So basically, what we have concluded from the previous computation is that if z has continuous partial derivatives of omega, meaning that fx and fy are both continuous, then the surface area of the z equals f of xy above omega can be computed by this formula. The area will be equal to the double integral over the domain omega, with the integrand being fx squared fy squared plus 1 taking square root dA. Okay, this is our new formula for a surface area for some region of the surface of a graph. Okay, we will generalize this formula to general surfaces in chapter 16, but for now, let us focus on the graphs. Okay, if that would be good, let us do some example. That is basically the whole concept of the section. You only have to understand that formula, and then we can apply it to various different examples. The first example is a classical one. Let us find the surface area for a sphere of radius r, where r is obviously a positive number. So the method one is actually a formula from the previous section. We should already know this from calculus 1 or pre-calculus, I'm not sure. So the precise section is section 8.2. We have the so-called surface area formula for the surface of revolution. So in this section, we have considered surface, which are not surface of revolution. It is a surface of a graph, and this is a very particular type of surface of revolution. And we know that by using a single variable formula, that whenever you're rotating a graph, a graph of a single variable function across some axis, and you want to compute the surface area of that rotated surface, then the formula would be 2 pi f of x 1 plus f prime squared, taking square root, integrating from the region you're interested in. And this is simply because that when you're trying to evaluate the surface area, then you can regard this small piece rotating around, in this case, the x-axis, right? And so the only thing you have to compute is the width of this band and also the circumference of the band. We know circumference is 2 pi times the radius, in this case, f of x. And the thickness of the band looks like the horizontal area or horizontal distance dx times slope, which is 1 plus f prime of x squared. So this small slanted infinitesimal term is 1 plus f prime squared taking square root dx. So this is the circumference, and this whole thing will be the thickness. So sorry, I should include the dx here. Multiplying those two guys and integrating, you will get your corresponding surface area. So in this case, the surface that we're rotating should be r squared minus x squared, right? So you have 2 pi square root of r squared minus x squared, 1 plus the differential of this guy, which is minus x divided by square root of r squared minus x squared, taken squared. And so miraculously, these two guys cancels out each other, and the remaining term is r. So integrating r from minus r to r, you simply get 4r 2r squared. So 2r squared multiplied by 2 pi is 4 pi r squared, which corresponds to the thing that we learned in maybe high school. The surface area for a sphere of radius r will always be 4 pi r squared. And this is actually a very ancient problem. As I mentioned here, it is already given by Archimedes in 200 years before BC. So yeah, even with calculus, we have various methods to derive this formula. So now let us provide a second method based on what we have learned today. So we're interested in the surface area of a sphere, right? That is a surface in a three-dimensional coordinate system. So we can regard it as a graph z equals to square root of r squared minus x squared minus y squared. That is the upper hemisphere, right? And we can integrate this guy on the region x squared plus y squared less equal to r squared. It is a circle of the domain. And we're interested in the whole surface area. So basically, due to symmetry, we can compute the surface area of the upper hemisphere and double it. And that'll be the whole surface area. So as I mentioned here, the area will be 2 times integration over the domain omega and zx squared plus zy squared plus 1. And then its computation. Zx squared is simply this guy. And zy, taking partial derivative, is again this guy. So after computation, you can see that this is actually sort of a improper integral because it's not really defined at, sorry, not 0, my bad. It is not really defined at when radius is r at a boundary. So let me make that precise. Okay. So you can see that when x squared plus y squared is r, this guy is not really defined, but it is still okay because you can regard this integral as if we're integrating everything below r and then we push the limit towards capital R. So due to the symmetry of this integration, I would recommend you guys to use the polar coordinate by changing x squared, x to be r cosine theta, y to be r sine theta. You'll find out that everything does not depend on theta, and that the denominator is square root of r squared minus r squared. The numerator is r, where you have an extra differential term r here. Don't forget this from section 15.3. We always have an extra r when you're performing the polar coordinates. So now replacing u to be r squared minus r squared, you have a corresponding formula, minus 2r dr. You have this very simple integral, and the final formula should still be 4 pi r squared. So just want you guys to be careful. This is actually an improper integral, but it is improper. The point of improper is at when r is 0, because the denominator will be 0, right? But it is actually fine because you have a nice singularity near this r equals to r, due to the fact that you can actually treat this guy, say t, and we push t towards r minus at the end of the day, and you will still get 4 pi r squared. Okay. Right. So that is the surface area for a sphere. We have to do it in two ways for now. We can use the washer-like method, which is introduced in the application of integration section 8.2. And we also used our new formula for the surface area to compute this directly. Okay, now let us do some not rotational symmetry region. So in this case, we consider the surface area of this polynomial z equals to 10 plus x plus y squared above this triangle with vertices 0, 0, the origin, 0 minus 2, and 2 minus 2. So this triangle is within the fourth quadrant, right? Okay, let us draw this origin, 0 minus 2, and 2 minus 2. So then we can apply the formula directly. We're integrating over this triangle, right? And the corresponding polynomial has differential zx, zy to be 1 and 2y squared. So in this case, I first do the type 1 region thing. I regard x to be having a constant bound. So x goes from 0 all the way to 2, right? And by fixing a particular x, y goes from minus 2 all the way to minus x. So that is this guy. And if you do the algebra, you will see that we're integrating this guy. Square root of 2 plus 4y squared dy. This is actually doable. You can do trig substitution, right? As I mentioned in the last video, you will want to apply the trig sub whenever you have a squared inside square root. So that is applicable, but it'll be kind of complicated if you actually do the algebra, which I encourage you guys to try to do it. However, this would not be a very wise solution. So let us try another way of equation. Suppose we consider this triangle as a type 2 region, meaning that we make the y domain into a constant bound, in this case, minus 2 to 0, and the x domain, whenever we fix the particular y, then x is within 0 and minus 1. So you have 0 to minus 1. We can immediately see how this is very beneficial because you have an extra minus y here, making u sub applicable. If we sub the u inside this square root 2 plus 4y squared, then immediately you have this differential term, which can be canceled out with this extra term minus 1. So at the end of the day, we get the surface area above this triangle of that polynomial will be 13 over 3 square root of 2. Okay, so this is sort of a nice example to demonstrate that you have to be careful with your order of integration, since Fubini tells us that those two integrals are the same. So make sure to choose a more simple one. In this case, regarding it as a type 2 domain will be simpler. Okay. And I think, this is a nice example. So I want to compute this surface area. And this is a example in our textbook. The surface itself is created by intersecting two cylinders. One is y squared plus z squared equals to 1, which is this yellow thing, okay, in this direction, in the x direction. And one is the cylinder x squared plus z squared equals to 1 in the y direction. So it is the blue thing here. After the intersection, you get this strange solid, and want to evaluate the surface area of the solid. So first of all, notice that this is a very symmetrical object, right? For the first step, we notice that it is symmetrical respect to quadrant, meaning that the first quadrant here, the second quadrant here, third, fourth, all of those quadrants actually have the same surface area lying above and below. So we can simply consider the first quadrant, okay? This is the positive x and positive y quadrant. So we know that when we're dealing with this blue region, when we're below y equals to x, then the region is bounded by the blue curve, x squared plus z squared equals to 1. And above the y equals to x region, you have the x squared plus y squared equals to 1. Because, basically in this case, y is larger than, I don't know how to say it, but at this region, when y is larger than x, then you always have this guy bounded below by this guy. So in that case, the yellow curve will be our surface of consideration. And in this guy, you have x less than y. So this guy is always less than this guy, making you want to consider the blue curve, right? Okay. So again, by symmetry, actually, you can consider only one of this triangle because this two actually give you the same surface area. So our whole surface area will therefore be the integration over this blue triangle having this multiple. So the first multiple corresponds to the fact that there's 4 quadrants, and the second multiple corresponds to you have above and below. So just like the spherical case, you have this above and the region below, right? Lastly, you have an extra 2 because of symmetry of this guy, and this guy. right? So in total, you have a 16 in front of your commutation. And the integral the surface that we want to consider now is z equals to square root of 1 minus x squared, right? So taking partial derivative with respect to x, and so this should be y. The first term will simply be square root of x squared minus 1 over, x squared minus over the 1 minus x squared. The second term is 0 because the thing does not depend on y. The third term is 1. Okay? And turns out that this is a really nice simple integral. It looks like this. And don't forget that we're parameterizing this region. In this case, I use x first. I regard this as a type 1 domain. X goes from 0 to 1, where for a fixed x, y goes from 0 to x. So then you're integrating this guy respect to y. So that is nothing because this guy is independent of y. So you have a x of x. And then this is very easy to compute. You use the simple u sub by the denominator, and you get the minus 2x dx, where the x can be canceled out with the extra factor x here. So at the end of the day, you get the formula for the whole thing to be 16. Okay? So basically, one of the p's here here will be of surface area 1. And you have 16 piece of them. Oh, sorry. Yeah, very correctly. Yeah, you have 16 pieces of them above and below. So therefore, you have 16 as the whole surface area. Again, this is actually a very ancient problem. This is called the Steinmetz solid. There's a particular name for this solid. And there is various investigation of this kind of solid, both by the Greeks, by Archimedes, which I mentioned before, and also the Chinese guy. He is called Zhu. But anyway, this is one of the computation of the surface area with a particular strange kind of solid, but it's still computable. You can use symmetry to reduce the computation heavily. Right. So this is a relatively simple section. Basically, the only formula you have to memorize is the surface area formula. Whenever you have a graph given by z equals to f of xy, you want to compute the surface area above some two-dimensional domain omega. Then you simply integrate over omega the integrand fx squared plus fy squared plus 1. And we have applied this to the spherical case, some case with respect to a triangle, and also the strange Steinmetz solids. Okay, as I mentioned, we will be seeing this again in chapter 16. In that case, we will see how we can generalize the formula to a more complicated version. And that version actually contains this particular case of the formula. I will see you guys in the next section. See you.